Hello everyone, good morning. Good evening, middle class. I'm just waiting for 2 more minutes. After that, I will start. During this problem solving session, if you have any question, you can ask in message section also. During this session, if you have any problem, you can also say your problem in the message section also. I will just start after 1 2 more minutes so that anyone many more can join. Then I will start. Okay, it's already 6:04. So I think that's enough. Anyone will not join. Mm. So I can now start. Uh, okay, so welcome to the new mm, problem solving session. This is week 4 assignment problem solving session. Sorry, week 6 assignment problem solving session. And myself, Amir Mundal, I am a PNR scholar of IIT Roorkee under Professor Thierry Yadav. I am doing the NPTEL course of assignments problems of NPTEL course of fundamentals and applications of dielectric ceramics. The course instructor is Professor Ashish from IIT Kanpur. Okay, so uh, we are going to discuss about the assignment problems. There are 15 problems. Um, you also have shown in every assignments last all 5 assignments. In this assignment also, only 15 problems are I'm going to solve and discuss the concept regarding the problems of week 6 and assignment 6. So, first of all, let's discuss what you have learned in week 6. Okay, what you have learned in week 6, impedance spectroscopy and dielectric breakdown. Next, although you have learned impedance spectroscopy in week 5 also, here is some more discussions has been also done in impedance spectroscopy analysis of and the importance of how impedance spectroscopy is important in measuring the correct dielectric constant versus temperature plot, and also dielectric breakdown, different dielectric breakdown processes you have also learned, and different questions have also been made based on these questions. We will also see that I will also discuss every concepts again so that you can understand every problem's basics concepts. Next, basics of nonlinear dielectrics. In the previous week, in week 5, you also have learned about linear dielectrics and nonlinear dielectric, difference between same, and how nonlinear dielectric concept have been arised. Okay, so nonlinear dielectric concept have been arised because of the nonlinear variation of polarization with respect to the electric field, temperature, or any other external forces. So variation of polarization uh, non-linearly, nonlinear variation of polarization, then the concept of nonlinear dielectrics have been arised. So you also have learned in these topics also, and many questions you will found here also. Next is piezoelectric effect. What piezoelectric effect is, how the strain and stress are generated, strains are generated due to the application of external electric field or mechanical stress. Okay, charges are developed due to the external mechanical forces. All these are case of piezoelectric effect. Many questions have also been done here, and different types of tensors and their behaviors regarding the piezoelectric effect have also been discussed also the week 6 assignments and week six lecture also. Next is pyroelectric effect, the effect of temperature on its polarization value and their corresponding tensor value and their corresponding electrostatic value. Hmm. This is also included in this week 6 assignment problems. Next, the thermodynamical concept. Thermodynamical concept means the free energy function and its variation with different thermodynamical properties like entropy, uh, electric field tensor, stress tensor. Okay, everything we will discuss also in case of piezoelectric and pyroelectric material. Okay, so let's start with question number 1. Okay, question number 1 is telling about the property of second rank tensor. Property of second rank tensor. Rank of a tensor. What is the tensor? What is a scalar? What is a vector? Okay, there are three types of measures. One is scalar, we know, is vector, tensor, and their rank. Rank 1, 2, 3, 4. Okay, we will say all of these. So you know about scalar, only magnitudes. It has only magnitude, no directions. Vector has a magnitude as well as its direction. Tensors form a matrix and it has also direction as well as magnitude, but it varies differently with different directions. Okay, so what is the general definition of tensor? What do we mean by the tensor? Tensor is defined as a set of 3 to the power r components. That is very important. We always measure 3 to the power r component. R is rank of a tensor. Okay, so a tensor is defined as a set of 3 to the power r components which describes a physical quantity. It should always be a physical quantity. The description of a physical quantity is represented by a tensor of different ranks. We see different rank and their different tensor with their different ranks, and therefore they show also a physical quantity. In addition, a tensor has to have a special transformation property also. Okay, everything you have learned in lecture section, just I am recapping. So it has also a special transformation property upon a change on the basis of the coordination system. Basis of the coordination, if the basis of the coordination system is changed from x, y, z to uh, x plus something x dash, y plus something z plus something. This is for Cartesian coordinate. Okay. Or polar coordinate. There is also polar coordinate. There is also cylindrical coordinate. Okay. Polar coordinate are theta phi you will see and their transformation. Okay. In cylindrical coordinate you also see um, rho, phi, and z and their transformation. So in any coordinate system, and the basis if the basis of the system is transformed, tensor also follows these types of properties. So okay, transformation we will see later, but we are now confining ourselves in the rank of the tensor. As previously we have written the 3 to the power as this is the uh, representation of tensor. Okay. If any quantity, tensorial quantity B or A, and its corresponding rank should be written in their subscript. Okay. So if there will be scalar, if it is scalar property, all scalar are also tensor with rank 0. Scalar are also tensor. Vector are also tensor with rank 1. So 3 to the power 1 means 1 component will be there. 3 components will be there. If 3 components will be there, then it will be vector form. In 3-dimensional form, we have seen that in 3 components. What 3 components are? In Cartesian coordinate, we know x, I cap, y, j cap, z, k cap. These types of coordinates, 3 components should be there. In case of polar coordinates also, in cylindrical coordinate also, we will see that there will be 3 directions, 3 components along r theta, r cap, phi cap, theta cap. Similarly, in cylindrical coordinate also, rho cap, phi cap, z cap. 3 components should be there. But what should be the components in a matrix form? In a matrix form, which is told as a second rank tensor. Second rank tensor. Okay. In second rank tensor, 3 to the power 2 gives us 9 value. Means there should be a 9 component. Suppose a tensor A, which is represented as I, J, then its 9 components should be written if Ij, this is a second rank tensor. This value is 2. Second rank tensor. Means 3 to the power 2 means 9 components should be there. So A11, A12, A13. Similarly, A21, A22, A23, A31, A32, A33. So in a matrix, this is a matrix. Okay. In a matrix, there should be a 9 components. 9 components. Okay. There should be 9 components. So the question is based on this topic, on this concept of tensor. So we will see the question on this is based on this concept. So in general, there are 3 to the power r components. If there are third rank tensor, we consider if we consider third rank tensor, then how many components should be there? 3 to the power 3 means 27 components. And in this 27 component or in these 9 components, there is a property called symmetry. Based on this each symmetry, based on this each symmetry, based on its symmetry, the component value 9 3 to the power r, this component value is will vary. So varying component value. Okay, this will vary. This will vary. This component value will vary. Okay. If- When we will see the symmetry operation in the tensor component, then we will see the components would vary on the basis of symmetry. In these cases, you can see that these diagonals are symmetrical. Okay, these diagonals are also symmetrical. So, based on this, there should be a component of three components if they are symmetrical. Along these diagonal will also present. Okay, we'll see it later. So, here is an example. You can see B I J K dot 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 N I J K N P Q R T into A means it is a also a tensor is also a multiplication of two tensors. It is also shown here. We will see here later that stress tensor. Ah, okay, piezoelectric tensor. So on the basis of this concept, on this multiplication concept, when we are taking I to R value up to U value, N up to U value, this is a total. We are taking the total values of rank concept. Then here it will be half and there it will be half. From PQR, where up to N is considered, then here it is up to N has been written, and from N to uh, from N to sorry, P to U in this cases here also written. Okay. If you see the example, then you will see. So A is a F rank tensor, G rank tensor. Okay. B is a G rank tensor. So A should be their summation rank tensor. So uh, B is equal to A into A. So it has rank F rank tensor. Okay. And it has, sorry, it has F rank tensor. And if it has G rank tensor, then its tensorial rank should be G plus F. Okay, this is the concept. So now see some examples like this is an isotropic. We also learned about that here. This is the susceptibility. Susceptibility. Okay, this is the susceptibility is related with polarization and electric field. So susceptibility tensor we can write. Uh, sus- we can write polarization as a tensor, electric field as a tensor, and susceptibility as a tensor. So this is a relation between vectors generally described by scalars, implying that the both vectors are parallel. Okay. So if this is in the case of isotropic material, where E and P are parallel to each other, isotropic material. Okay. You can see that for electrical susceptibility concept, E and P are parallel to each other when no electric field is applied. Okay, when electric field is applied, then P is directing along this and E is also directing along this. So P is parallel to E. Okay, but in these cases, E is not parallel to E in these cases. So there is a, you can see there is a resultant vector along this direction, resultant vector along this direction. So this is the case of anisotropic. Isotropic and anisotropic materials are divided on the basis of their anti-parallel and parallel arrangement of P and E. Okay. So on the basis of this, when P and E are parallel, P and E are parallel, their uh, rank of this tensor It will be same also that new. So what will be the uh, this is the rank. What will be the rank of chi? The rank of chi will be new into new. Okay. Therefore, and in these cases, the rank of for this is symmetric. Isotropic. This is anisotropic cases. So in these cases, H plus nu should be there. Okay, in two-dimensional cases. And in general, this is a second rank tensor. So 3 to the power 2 means 9 components should be there. Okay. And it will, we can see that their matrix form can be uh, dissolved into this, into each of these form. And this is the abbreviation that J lies from 1 to 3. This is the Einstein notation. Okay. I and J both have lies in 1, 2, 3. So this is the abbreviation version where only J is varying. But in Einstein notation, summation, we do not use summation. Only we use I and J value and their variations. We don't like summation symbol, summation over, okay. So, okay. So this is the for second rank test. And this is a uh, triangular and for prismatic variation or prismatic representation. Okay, prismatic representation. Representation of strain, polarization, electric field. Okay, strain, polarization, electric field, temperature, etc. Okay, so when stress is related with strain with elasticity. Polarization, stress polarization related with direct piezoelectric effect. Okay. Similarly, thermal expansion, temperature and strains are related with thermal expansion. Enthalpy and temperature are related with heat capacity. Okay. So, and in case of pyroelectric effect, polarization and temperature are related. And electric field and susceptibility are related with electric field are related with susceptibility polarization. So there is one. How many types of properties are there? 2, 3, 4, 5, 6 properties are related, are shown in this diagram. Okay. Okay, let's try to find the answer of this question that the property of a second rank tensor, the property of second rank tensor implies that it constitutes a matrix of 9 components and it requires minimum 2 directions to describe it. Okay, minimum 2 direction to describe it. A, I, J, this also signifies 2 directions. I is varying here and J is also varying here in this direction. 1, 2, 3. Here 1, 2, 3. So A, I, J. How we 1, 2, 3. Okay. So A, 3. We can write in a 2 direction as we have. So this is one direction, along this direction, this is also one direction. So 2 directions should be there. And it constitutes 9 matrix. Okay, 9 matrix, 1, 1, 1, 2, 2. But I have shown it. Okay, that's 9 matrix should be there. 9 matrix should be there. Okay. So we can go to the next question. So B and D are correct answer in this question number 1. And for question number 2, this is also on the basis of tensorial formula. So you can now answer the question of not just read the question that consider the equation p p dash means you have to fill the what will be the um, value of rank of t. What will be the rank of t where p is equal to d into sigma. Okay, P denotes polarization, D denotes piezoelectric coefficient. Okay, and sigma denotes stress tensor. Okay, so polarization is stress. Polarization is related to stress in which property? This is a piezoelectric property. Okay, this is a piezoelectric property, and the corresponding D value, the tensorial value represents the piezoelectric coefficient. Okay, so how they are related? You can easily uh, uh, say that what will be the rank of P by just seeing the P value and P. What will be the rank will be? Yes, D, J, K, L and sigma K, L. Okay, so it, as I have previously told in the previous question, that the rank of this, the rank of this, the proportionality rank should be determined with the summation of two D's, summation. Okay, so J is summed up with K, J is summed up with KL. So J should be there, here only J should be there, and if J only, we are using only J, means its value, n value of 3 to the power r value is 1. Okay, only J are using, not using. If we are taking KL, then R value should be 2. So R value is 1 here. And 3. So 3 components should be there. But this is a vector. R means this is a vector. Okay. This is a vector. R means this is a vector. Okay. Okay. Everything going well or not? Just 1 minute. Saying everything is running well or not? Okay, everything is fine. Just okay. So this will be a vector of rank 1. So this is a tensor of rank 1, means this is a vector. Option C will be correct, and the value of E, the rank of P will be J. Okay. So superscript of P will be J. Okay. Now, I'm just discussing something about the piezoelectric effect. This question is based on the piezoelectric effect and its concept. Okay. So just let's see. Uh, what piezoelectric effect tells us, what piezoelectric effect is. The charge induced by the application of external stress. Charge induced by the application of external stress is piezoelectric effect, can be expressed as di equal to dijk equal to into sigma ij, sigma jk. And you can see that this I, the and this is jk. We are applying external so piezoelectricity polarization is generating due to this sigma, external stress due to this stress sigma. Okay, and its rank is jk and its rank is I. So the proportionality constant D is proportionality constant. Its rank should be I, J, K, the summation. Okay, as we have already told you. This is piezoelectric coefficient. This is a third rank tensor on the basis of three. And so a subscript, its unit is Coulomb per Newton. Just by Coulomb per Newton means microcoulomb per centimeter square or Coulomb per centimeter square. Coulomb per centimeter square um, divided by sigma. Sigma is stress. Okay, so stress is nothing but uh, this is divided by Newton per meter square. This is a pressure. Pressure Newton per Coulomb per centimeter square. Newton per centimeter square. This is Coulomb per Newton. Okay. So this is a stress. Stress is nothing but pressure. Okay. Mechanical pressure. Mechanical pressure. Okay. And the converse piezoelectric effect, we can also tell converse piezoelectric effect means just apply electric field, strain is generated. That is, strain is generated. Apply field, applied field. So strain is related with field, applied electric field. Strain is generated due to applied electric field. So what will be the proportionality constant here? Proportionality constant here, we are taking it as a D, and if it is two rank tensor, if it is electric field is one rank tensor, then it is Kij. It should be Kij, means the transpose of D means they are just transposed to each other, where K value is alternating to each other. Okay. So this is the concept you also have learned this. So I am just uh, recapping this stress tensor or stress tensor, strain tensors and their concept. Okay. Sorry. Can see the stress tensor, stress tensor and its component, how in three directions so they are varying. Here in 1, 3, this is 1, 2, this is in this direction and 1, 1. Okay. So sigma ij component is sigma 1, 1, 1, 1, 2, 1, 3, 2, 1, 2, 3, 2, 3, 3, 1, 3, 2, 3, 3. Okay. So in these cases, you can see sigma 3, 3, 3, 2, 1, 3. Okay. So they are in each direction, each x1, x2, x3 direction, they are plotted taking these three at each surfaces and each how they are varying. Okay, you can see. And here there are total 9 components, but 3 are normal components. 3 are called normal components. These are called normal components. Okay, you can easily see that in this surface, these components is normal to this surface. This is the normal to this surface. This in this surface, sigma 2, 2 is normal to this surface. And in this surface, sigma 1, 1 is normal to this surface. Okay. So they are the normal components. And the 6 other components, these 6 other components, these 6 other components means this, and this, which are just parallel to the plane, parallel to the plane. These are parallel to the plane. These are called the shear. There was a shear component. Okay. Shear component always parallel to the plane. shear components are always parallel to the plane. So we have divided 9 into 9 components into 3 plus 6, normal and parallel to the shear condition. Condition 2 is in static with the immediate requires there are 3 certain relationship shear components. If this is a symmetric second rank tensor, then shear components, as I have previously told, that there must be sometimes there should be symmetry in their components. If sigma is equal to sigma ji, means symmetry is present, means sigma 1 2 equal to 2 1, and see sigma 1 2 and 2 1. This is sigma 1 2 applying in this surface, and this is sigma 2 1. They're just like same. Okay, symmetry. There is a symmetry, you can see. So they are symmetric. Just I and j value are alternating to each other. Okay, alternating to each other. Okay, they value are alternating. See the symmetric second rank tensor. Okay, now we can answer the question that this is a vector and their corresponding concept has also been cleared, teacher, please. Okay, now we are moving forward to the question number 3. Question number 3, this question number 3 is telling about the direct piezoelectric coefficient. Piezoelectric coefficient are related to the mechanical stress and polarization. Okay, this is a third rank tensor. I have already discussed, you will also learn it, that this direct piezoelectric coefficient is a third rank tensor. Means it has third rank tensor. What is the meaning of third rank tensor? Means it has 3 to the power 3 components. Means 27 components should be there. 27 components should be there. Considering stress sigma ij as a symmetric tensor. So sigma is a symmetric tensor, means sigma 1 2 equal to sigma 2 1, means ij equal to jr. Okay. Then sigma 2 3 equal to sigma 3 3 2, sigma or 2 or 3 1 2 2 3, and sigma 3 1 equal to sigma 1 3. Okay. So 6 components should not be there. 6 components should not be there. Minimum required number of tensor components for direct piezoelectric coefficient. Okay. Yes, for minimum number of components, what should be the minimum number of components now? In a third rank tensor, but sorry. Yes. This is sigma symmetric. Sigma stress is symmetric. But for you can see the linear relationship between this is the direct piezoelectric effect. Dijk, just this is a summation of I and jk, and we are writing Ijk. Coulomb per Newton is a third rank tensor. So for direct piezoelectric effect, Pi is generated by Tjk stress. So Pi is generated Tijk and Tjk. Okay. So this is a rank 1 tensor, this is a rank 2 tensor, this is rank 3 tensor. For 3 dimensional we have seen, and this is a symmetric tensor, reducing the number of independent components from 9 to 6. Okay, so independent component is 6 independent components. So for in the space of 3 then we are using 6 into per Pi. I value is varying from 1 to 3. Okay. And this will consider as a 3 into 16, and I value is considered as 1 to 3, and this will give us the 18 value. Okay, this will give us the 18. The required number of tensor component is 18, not 27, not 27. Okay, because of the symmetry consideration of this sigma. Okay, symmetry consideration of sigma giving the value 18, not 27. Okay, question number 4. In orthorhombic crystal system, which of the point group represents polar group? Which of the point group represent polar group? Okay, many things have been given here. In orthorhombic crystal system, which of the point group represent polar group? So you must have divided the point group. Okay, just see, you have also learned in class, in lecture class, that classification based on crystal glass classes. Out of total 32 crystal points groups, there are 32 crystal point groups. How? 32. 32 crystal points groups are there. So out of total 32 point groups, 21 are non-centrosymmetric, means there is no center of symmetry. If atoms resides here and the coordinate is like, then this is called the center of symmetry. So center of symmetry, if this symmetry do not lie, then we call it non-centrosymmetric material. Means crystal do not have the center of symmetry. Okay. So the centrosymmetry can, on the basis of centrosymmetry and non-centrosymmetry, 21 are what? Non-centrosymmetric. So how many are symmetric? Center symmetry. 11 have center symmetry. This is centrosymmetry. 11 has centrosymmetry. 21 has non-centrosymmetry. Okay. Inversion of point, as I have told that. So there are different crystal types, 7 crystal types we know: cubic, tetragonal, orthorhombic, hexagonal, trigonal, monoclinic, and triclinic. 7 crystal system, you already know it. There are 7 crystal system and their point group, 32 point group. Um, so centrosymmetric point groups, there are 11 centrosymmetric point groups, non-centrosymmetric point group, there are 21 non-centrosymmetric point groups. Total 32 point groups are there. So in case of cubic, you can see for non-centrosymmetric, two cases arise: polar and if any material or any atom shows symmetry. This is centrosymmetry or non-centrosymmetry. In case of non-centrosymmetry, means the balance is not occurred there. If there is no balance to occur, then there should be a polarity. There may be some polar or may not be some polar. If their polarity exists, then it is called polar molecule. And if there is no polar, that is non-polar molecule. Okay, so the question is based on the orthorhombic cases. In case of orthorhombic cases, okay, you can see that in orthorhombic crystal, each of the point group represents polar group. So in orthorhombic cases, you can see one is at centrosymmetry and one is polar and one is non-polar. This represents non-polar, Mn2 represents polar, and 3mm. M means mirror. Okay, M represents mirror reflected in the crystal system, mirror reflection in the crystal system. Okay, so based on this, okay, there is another information also that in non-polar cases where we find 20, in non-synchrometric cases, we find 21 point groups and one point group from non-polar cases 433, 432. 432 is not considered, and all the other mean 20, all other 20 point groups exhibit piezoelectric effect. So this is also important for piezoelectric effect. 20 only 20 point groups exhibit piezoelectric effect, means upon application of electric field they exhibit strain. Piezoelectric effect has two different types. One is upon application of electric field it exhibits strain, and next is upon application of external stress, charge develop on the faces of the crystal resulting in induced electric field. So two different types of piezoelectric effect is generated in the body, and out of these 20 non-centrosymmetric point groups, 10 belongs to polar crystals. So out of 20, 10 belong to polar crystals, and other 10, 11 out of the 11 belongs to these non-polar crystals. Okay. And crystals which possess a unique polar axis and axis showing different properties at the end. Okay, this is called polar axis. So you have learned about piezoelectric effect, means upon application of external electric field, upon application of external one strain is generated. Next, upon application of mechanical stress, external stress, charge is also developed on the each faces of the crystal. Now, so these crystals can be spontaneously polarized, and polarization can be compensated through external internal conductivity of Wiener tunneling field. This is another topic. So what is spontaneous polarization? Spontaneous polarization depends upon temperature. The spontaneous polarization. Okay, this depends upon temperature always, and in these cases temperature has arisen. If a change in temperature delta T imposed electric charge is developed. So with the electric charge is developed, on the face of the crystal perpendicular to the polar axis. This is called pyroelectric effect. So pyroelectric effect always depends on temperature, and the change in temperature creates the charges on each faces of the crystal lattice. So all 10 classes of polar crystals. So this is pyroelectric is a polar crystal. This is a non-polar. This is polar. But piezoelectric is non-polar. Okay. In some of these polar non-centrosymmetric crystals, the polarization along the axis can be reversed if this polarization. Now, okay, upon application, okay, this is also polar, so they are also polar molecule, okay, because they are polar molecule and they are non-polar molecule. Mn2 represents polar form. This is polar form. Okay, because charge is formed and the direction of electric field is caused by this induced charge. Okay, so these are the polar molecule, and these polar molecule shows piezoelectricity, pyroelectricity, and ferroelectricity. Also, ferroelectricity have much one more property of ferroelectricity is its reversal of direction. Means P and application of P. This is telling about the pyroelectricity. Okay, but if is polarization P E with the direction of electric field, if polarization reverses its direction, that is the main point. This polarization reverses its direction, reverse direction. Okay, then it is called the polarization. Okay, in a this is then it is called a ferroelectric material. So on the basis of this concept, we can say that all ferroelectric materials are pyroelectric materials. All pyroelectric materials are piezoelectric materials, but all piezoelectric materials are not pyroelectric materials, and all piezoelectric materials are not ferroelectric material, but all ferroelectric materials are pyroelectric and piezoelectric materials. This is a clear diagram of representation of diagrammatic representation of ferroelectric, pyroelectric, and piezoelectric material. Okay. Okay. Now you can see the question and now answer the question that in orthorhombic cases, point group, which point group represents the polar group? This is the answer Mn2. This Mn2 represents the polar group. Okay. Okay, now we can move forward to the question number 5. Question number 5 is telling about electrorestriction. There is also a property beside piezoelectricity, pyroelectricity, and ferroelectricity. Electrorestriction is also a property. So you also have learned piezo, pyro, and ferroelectricity. And you are learning about electrorestriction. This includes everything. Okay. So and in these cases you have learned you have seen that you have seen that third rank tensor Dijk has been observed in piezoelectricity. Okay, but in these cases we see that rank 4 tensor is also observed here. So let's try to understand what electrorestriction tells about. Okay, so electrorestriction is a property of dielectric material which is caused by displacement of ions in the crystal lattice upon being exposed to an external electric field. So, if displacement of ions V. Okay, displacement of ions. So, ions are displaced. This causes the electricity linked to enharmonic effects. Positive ions will be displaced. So, plus ion and negative ion. These cation ions are created due to the electric field. So, positive ions are in the direction of the electric field and negative ions are attracted to it. So, negative ions will be directed in the opposite direction of the electric field. And positive charges are accumulated on each circuit, on which area negative charges are accumulated on this area, and it at a distance d, it and an overall strain elongation in this direction of the field. So there is a disbalance of charges, and this disbalance creates a elongation in the direction of the field. Okay, and the thickness will be reduced. Thickness will be reduced. So d, the thickness, if the thickness is d, d will be reduced in the orthogonal direction, characterized by Poisson ratio. Okay. So how do they um, strain ratio of the deformation of original wave is proportional to strain is proportional to what? The square of the polarization. Strain is proportional to the square of the polarization. This concept we have to use in the tensorial form. So, what is this is the tensorial concept. This is the electrorestrictive coefficient. This is a 4-rank tensor. Rank 4 tensor. Due to which? Due to this 2-rank tensor and this 1-rank tensor. These two because one due to positive, one due to negative charges. Their direction are different. This different creates polarization at each directions, and this creates a elongation in the material. Elongation in the material, and This is represented in this way. So Q is a representation of electrostatic and electrostatic tensor satisfies this relation. Uh, that is nothing but the double derivative of epsilon ij, that is the strain tensor. Okay, rank 2 strain tensor and the derivative of partial derivative of pk and pl. Okay, so electrostatic is a the related piezoelectric effect occurred in the particular class of dielectric. Electrostatic applies to all the crystal symmetry, where we have seen that the piezoelectric, pyroelectric, and non piezo, pyro, and ferro, they only occurs in polar system, but it also occurs in non-polar systems. Okay, is electrostatic. So piezoelectricity is also electrostatic in the ferroelectric material. Okay, so electrostatic friction, piezo, pyro, and ferro. You can see this concept. But electrostatic steam is also contains non-polar molecule also. It's a quadratic effect, unlike piezoelectricity, which is a linear effect. Okay, and also piezoelectric coefficient is a third rank tensor. Okay, so this is a piezoelectric coefficient ijk, where ik and jk, and reduced number of India. You have also seen that 27 to 18 reduced number of piezoelectric coefficient. Okay, it has a symmetry in quartz, which is trigonal. There are only two independent coefficients in the tensor. Okay, so piezoelectric coefficient can be interpreted as a piezoelectric charge coefficient. That is the piezoelectric coefficient Bijk. Tk is the mechanical stress, okay, developed, and the charge developed. Okay, so electrostriction is different from piezoelectric effect. So you know piezoelectric effect. You also know about the electrostriction. Now we can. So first option telling about electrostriction coefficient is a third rank tensor. No, it is a fourth rank tensor. So first option is incorrect. Electrostriction coefficient is a fourth rank tensor, while piezoelectric is a third rank tensor. Electrostriction is found only in those materials which lack a center of symmetry and are polar. No. So if found in all, no restriction is there in all material, found in every direction irrespective of symmetry. Okay, so in every dielectric material irrespective of symmetry, you can find. And just saying that everything is going well or not. Okay, so you can see that electrostatic found in every material. Okay, everything are going fine. Okay, so electrostatic friction is found in every dielectric material irrespective of its symmetry. Okay, next question number 6. Direct and indirect piezoelectric coefficients are thermodynamically the same. They can be expressed in terms of Gibbs free energy. So Gibbs free energy, we also know about this. Gibbs free energy as and Gibbs free energy. Gibbs free energy, what we will see in which how many factors the give on how many factors Gibbs free energy depends. Okay. Direct indirect piezoelectric effect Dijk and P uh, I, A, J. Okay. They can be termed as gives free energy depends on EK, how EK and sigma ij varies, and their variation with G how produces sigma ij. So sigma ij each epsilon ij, this is a polar from polarization. It depends on sigma, it depends on E, it depends on heat, it depends on temperature. On dependency of this, so epsilon ij is a function of epsilon ij is a function of what? Sigma kj, ek, hk, and t. Okay. So on this basis of similarly, these has also been expressed. So first and second law of thermodynamics. Just internal energy equal to work done plus um, the external work. Okay. Internal energy. So on the basis we can sigma ij should be there, polarization should be there, heat would be there, entropy should be there, and delta G is nothing but U. This. So from on the basis of this, we can see that delta G finally. So it will vary as sigma ij, k, hk. This is simple partial derivation of its dependency of different parameters. Simple partial derivation. Okay. From this, you can easily calculate epsilon ij. Just uh, comparing these two. So so this what? This denotes epsilon ij, and this denotes pk, this denotes zk, this denotes s. Okay. So what is the main point? Chi kj, x kj, chi kj. This is the dielectric susceptibility. Chi kj is nothing but dielectric susceptibility is nothing but polarization and dj. We have a kj eg, from where the dielectric susceptibility arises. And on the basis of this, we will find this. And pk, what pk denotes? Pk denotes del g del ek, pk denotes del g del ek. Just put this value del g del ek minus. Okay. And you will find this, del g del ek and del e. That is nothing but del p del ej. That is xj. So this is a symmetric tensor also. This is a symmetry. Okay. But what is the piezoelectric case? In case of piezoelectric case, is uh, that is the electric models. But what is the piezoelectric case? Piezoelectric case, you know, del P del sigma. That is the piezoelectric case. K I J should be there. So what? So the just ratio should be the should denote del Pk del sigma j, denote the piezoelectric coefficient stress, and this piezoelectric coefficient, and Pk is denoted as del G del Ek, del G del Ek, just put del G del Ek, and if its reversal direction Ij and K gives you del, so del of Pk and del of sigma j gives you epsilon Ij, that is sigma Ij. Okay. So on the basis, you can just say that this term, is d Ijk. This term is piezoelectric coefficient. What direct piezoelectric coefficient, direct indirect piezoelectric coefficient, this term, which Ek consists of Ek and sigma Ij, both with the dependency of G. So this is a piezoelectric coefficient. Okay. And pyroelectric. Okay. So you have learned about pyroelectric effect, electrostriction, and del G, which is based on U, ds, and du, which is nothing but this and this electric field and this. So del G, just finally, just put the du value, this du value here, and you can see that this term and this term will be cancelled out, from this term and this term, and you can now finally item. So from this entropy you can calculate entropy. Everything have been discussed in your lecture class. I am just telling that how entropy is related. Entropy is related to temperature, where x and e are constant. T and d are constant, where strain is generated del G, and how charge density is varying this. So, and ds, s is a function of temperature, x, ij, and e. So, on the basis of this, now just compare these two relations. Okay, and d is also there. There are four variation. One is s, t, xi, and e. They each equally dependent to each other. Okay. So what is the variation in g in respect of g? So d, I, j, k, t, x. Everyone should conclude. Everyone should conclude. And in this case, del I, j, k, just put the value of x, I, j. Just put the value of x, I, j. Okay, just put the value of x, I, j. You will find the del G, del ek. Del G, del ek. Okay. So, and this is the main answer of this question. That now then tell that del 2G, del ek2, del sigma I means it depends on ek and sigma ij. This is the answer. Okay. Now question number 7, that discounting the effect of crystal symmetry, the number of tensor components for elastic stiffness are number of tensor components. Okay. Uh, Elastic stiffness. So what is elastic stiffness? Elastic modulus. Strain is second rank, stress is second rank, elastic stiffness is fourth rank tensor. Okay, elastic stiffness is fourth rank tensor. The fourth rank tensor means 3 to the power 4 gives you 81. But this symmetry consideration, this symmetry consideration gives you 31 independent components. If this is symmetric, means all the I, J, K, L value, I, J, K, L value will be symmetric. J, I, K, L value will be symmetric. Means I, J, K, L. They will clockwise rotate to each other. Then J, K, L, I, J, K, L, I. Then I, J, L, K. So clockwise they will rotate and reduces the total number of compounds. Okay, so discounting the effect of crystal symmetry, just reduce the crystal symmetry. Uh, just reduce this crystal symmetry. S, I, J, K, L, S, J, L, I, S, L, I, J, S, L, I, J, L. Okay. Just reduce this crystal symmetry and find the value of 36, not 81. 3 to the power 4 mainly gives you 81, but this is not true here. Only 36 will be there due to this symmetry consideration. Okay, so the answer will be 36. Okay, just discounting the effect of symmetry. Okay, now this is a question from impedance spectroscopy. Okay, this is a question from impedance spectroscopy. Elastic modulus is related to complex Z. How? Just elastic modulus related to complex modulus in this way. J omega C naught Z star. J omega C naught Z star gives you the uh, elastic modulus value. You can see that this is a complex form. All these are, this is a complex form. Means it will be have a real part, it will be having a imaginary part. Real part, so, and we are just multiplying j omega c naught with this j star. This is also a complex. This gives only z dash z dash. So z double dash part 2jj multiplication gives and minus with minus gives plus value. So omega c naught value into z double dash. So this is a imaginary part of z, that this is a real part of z double dash. Okay, but then this total gives you the real part. This total gives you the imaginary part. So imaginary part of z dash gives you the real part of m star, and real part of z dash gives you the imaginary part of m double dash, m star. So because of this multiplication of I factor, okay, multiplication of I factor. So what will be the answer? Answer will be I omega c naught into z star. Okay, just see another calculation how it has been generated. Okay, that m star is when this is the dielectric permittivity. Permittivity. Okay, this is inversely proportional. Permittivity is also complex. Okay, complex permittivity. Okay, so complex from this complex permittivity, we are getting this value as a complex value. So now, what is the importance of using m star? We are just easy okay with epsilon star for evaluating the dielectric constant value, but what we require the m star value and z star value. Z star value is fine at a low frequency region. At a high frequency region, sorry, Z star value as a fine as a high frequency region. Fine in high frequency region, but it is not applicable to low frequency. That's why we have um, modulated the impedance spectroscopy value to some extent with the multiplication of j omega c naught, so that we can find just we are multiplying omega value. We are multiplying omega value. So we are just increasing modulating the value of m z dash z star. That's why we are getting m star for low frequency region. To see the evaluation of low frequency region, its contribution of low frequency region, so that we can just sum out of we can just evaluate all the spectrum of frequency and its contribution on dielectric property. Okay, that's why that is important. Moreover, it can also be expressed in terms of derivatives. Okay, so j omega z dash. That's this is the concept of m star, where m star has been taken from z star impedance spectroscopy. Okay, so next we are forwarding to question number 9. Okay, just wait for 1 minute. I'm just taking some water. And at that time, you are just question number 9, only 6, 7 questions are left there today. Okay, going well. So, please if you have any if you have any question, you can ask me in the message section also. Okay, okay. Let's try to find out the question number solution of question number 9. That's pyroelectric coefficient. Pyroelectric coefficient is a vector, scalar, second rank tensor, third rank tensor. Pyroelectricity is nothing but the induced charge by temperature change. Induced charge means polarization with the temperature change. Okay. So, what will this give, or D, or sorry, pyroelectric coefficient equal dt. Okay. So it's a first rank tensor. This is a scalar. Okay. It's a vector, one rank tensor. This is just nothing but the psi delta t. Okay. This is nothing but psi. This is pyroelectric effect, pi dt, and this gives you the pyroelectric coefficient, that is the pyroelectric coefficient, and this is uh, I means this is 1, means 3 to the power r, means r equal to r. This gives you the first rank tensor. This gives you the rank 1 tensor, rank 1. And rank 1 tensor is nothing but the vector, which has 3 components. Okay. So this is a vector quantity. Pyroelectric coefficient is a vector quantity. Okay. So this is a vector, and it's not a scalar. We can move forward to the question number 10. Okay. Where dielectric breakdown is manifested by, there are 4 options has been given there. Sudden increase in conductivity of dielectric material upon application of large electric field, thermal breakdown due to the heat dissipation, drastic increase in the capacitance value, gaseous discharge in the dielectric material at high voltages. Okay. So there are different types of dielectric breakdown in a dielectric material. What breakdown means? Breakdown is nothing but the breaking down of dielectric property, breaking down of dielectric materials from its insulating property. Okay. If insulating property is lost, the material becomes conductive, means a electrical conductivity should be generated after the breakdown. So there should be a limit of current. Okay. Limit of induced current or leakage current inside the material. After that limit, after the application of electric field, temperature, or anything external forces, the dielectric material behaves as a conductive material after the breakdown field. That is, this limit is called the dielectric breakdown limit. Okay, just read this. Every material is bound to fail or break down under certain conditions. Short circuiting, it was the dielectric. It means short circuiting means accumulation, generation of more charges after a certain limit. So dielectric breakdown occurs when the electron density in the conduction band becomes very high during the application of an electric field, such that conductivity increases. That is the main point. That electron density in the conduction band, this is the valence band, and this is the conduction band, and here electrons are present. And if electrons goes to the conduction band from valence band to the conduction band, then there is a electrical conductivity should be generated there. Okay, so becomes very high during the application of electric field. Okay, rapidly resulting in a permanent damaging of the material. So this breakdown damages, permanently damages the material. Okay, damages in the sense that damages its insulating property. However, it is easier to measure and talk in terms of uh, the electrical current, which is anyway is represented in electrical density. This is the current density, current per unit area. Okay, so you can see that with the increment of electric field, this is almost constant. And at a certain point, that is E critical. At a certain electric field, the material breaks down its insulating property. Is broken. Insulating property is broken at a certain point. Okay, so this is the limit of electric field where our, our dielectric breaks down. There are different types of breakdown mechanism. One is intrinsic breakdown, thermal breakdown, avalanche breakdown. Okay, so what intrinsic breakdown is? Intrinsic breakdown mechanism is based on the lattice ionization. Means intrinsic means this breakdown occurs inside the material. This breakdown occurs inside the dielectric. How? It's based on the lattice ionization. When ionization occurs, means the positive anion and the negative cations are generated. And the subsequent increase in the electron temperature. Electron temperature increment also breaks down the lattice ionization. Okay. Actual breakdown field is larger than the critical breakdown field. If we are applying the actual breakdown field, the larger than the critical breakdown field. That is the first incident. A dielectric breaks down needed to cause a critical breakdown at a temperature. Okay. And in the intrinsic breakdown, you can also see is field dependent, and here applied field determines the electron temperature to reach critical level for breakdown. The break time is very short, smaller than millisecond, suggesting that process is electronic in nature. It is also independent of the sample or its geometry or its waveform type. Okay. and it is a purely material dependent process. Purely material dependent process. It is purely material dependent process. So intrinsic breakdown purely depends on intrinsic properties and how it's breakdown in very short time. It has some it independent of sample or its sample geometry or waveform type. Okay, so that's our for intrinsic breakdown. Okay, and what thermal breakdown tells us about it occurs due to heat dissipation in the sample. Occurs due to heat dissipation in the sample due to the current flowing through the defective parts. In a dielectric material, it consists of grain boundaries, okay, different grain boundaries. There should be impurities also. There should be a vacancy also. There, there may be a vacancy also. Okay. So all these properties, all these things, all this consideration, uh, also all these considerations affects the dielectric material when in the case of electric field application. So heat dissipation also occurs because of the current flowing in this defective part. They are easily they are easily polarized. As you know, for air, it has dielectric constant of 3. For barium atom, it has dielectric constant of nearly uh, about 300. So in this vacancy part of impurity part, it easily breaks down. So this affects the dielectric material. I will define. Okay. So leads to subsequent increase in the conductivity. And when failure, this increment in the conductivity, this increment in the conductivity increases heat, produces heat. Okay. So it is very common process in the most bulk materials. Bulk materials, thermal breakdown is developed in bulk material also. It depends on the speed of the application of the feed. Okay. It is observed between room temperature and 300 degrees centigrade. So it's very important point at the 300-degree temperature. Ambient temperature means room temperature. Okay. Determines the electron temperature not by electromagnetic field. Rate of application at the field region is also an important factor. Okay. And avalanche background is nothing but large accumulation. And okay, thus more electron leading to the large increase in the time. Just this is which can further lead to a multiplication process. Electric field in a sample leads to energetic electrons. And there is other factors also which affects the breakdown mechanism in a material. That's a dielectric discharge. Okay, electrochemical and or mechanical breakdown also. So they also affect the material. Dielectric discharge. What is dielectric discharge? Small pores, as I already have told you, small pores which are always present in the sintered dielectric material. In a sintered dielectric material, pores always present. The field strength is higher than the average field, and as a result, microscopic arc discharge may be initiated at a direct material. That's a very important point. And electron shines from the discharge bombard inner surface, erode it. As the pores grow, current in the arc increases, leading to an increased sample temperature, eventually leading to failure. Another failure breakdown is electrochemical breakdown. This occurs due to transport of conducting material due to the presence of local electrochemical current paths or defects in the interior of the dielectric, leading to the overall increase in the sample conductivity and then failure. Okay. It is assisted by suitable atmospheric conditions such as humidity and pH condition also. on the basis of this concept, we can now answer the question that dielectric breakdown is manifested by which is option number A, that sudden increase in the conductivity of a dielectric material upon application of large electric field. Okay, application of large electric field, the sudden, this is also called a dielectric breakdown. Thermal breakdown due to the heat dissipation. This also is a term. Heat dissipation, thermal breakdown also considers the dielectric breakdown process. And the gaseous discharge in the dielectric material at high voltages. Gaseous discharge due to the force. Okay. Center. After center. Or option number 3 is drastic increase in the capacitance value. This is not correct. So A, B, B. 3 options are correct. Okay. Now, see question number 11, that ferroelectric materials have following attributes. Are they piezoelectric? Are they non-centrosymmetric, polar, piezo, non-centrosymmetric, polar, and reversal of axis? Okay. Okay. So let's see. I already have discussed about different polar point groups. Okay, this is centrosymmetric, this is non-centrosymmetric. It is divided into polar and non-polar groups. For each cubic crystal, 7 cubic crystals. Okay, this is and polar group contains 10, total 32, it contains 10, it contains 11, so that is 21, and this contains 11. Okay. So, and for ferroelectric material, it is a non-centrosymmetric crystal. So in this group, non-centrosymmetric crystal is a non-centrosymmetric crystal, and it is also a polar. It is a non-centrosymmetric crystal. Means in this group, this exists. Okay. Also, the polarization axis along the polar axis can be reversed, as I have already told. P and B with the application of electric field. P can be reversed with the application of electric field. So reversal of P can also be done in this ferroelectric material. And also, you also know, you are also aware that ferroelectric material, all ferroelectric materials are piezoelectric materials, all ferroelectric materials are piezoelectric materials also. Okay, from this it is a very important diagram for understanding ferroelectric, piezoelectric, and piezoelectric materials. Now we can answer the question that ferroelectric materials have different attributes. Number 1, all ferroelectric materials are not piezoelectric. That is incorrect. That is incorrect. All ferroelectric materials are non-centrosymmetric. That is a correct answer. Okay. So non-centrosymmetric. This is a correct answer. Next, all ferroelectrics are polar in nature. This is also correct. This is also correct. That all ferroelectric materials are polar in nature. Okay. Next, the polar axis of the ferroelectric material cannot be reversed. No, it can be reversed. E and A are E and E. Both can be reversed. Okay. It can be reversed with the application of electric field. Okay. This is not correct. So in this question number 11, B and C options are correct and another 2 are incorrect. Question number 12. Okay. Now representation of strain field. This is nothing but strain comes from application of electric field, application of the generate charge, and this charge generates uh, strain. Okay, this charge generates strain. Okay, you already are aware of this relation, this delta G, where epsilon I j delta sigma j, this is electric field and polarization, this is heat dissipation, and this is entropy. So G is a function of sigma I j E Q H and T. Okay, on the basis of this, just partial derivative, partial derivative of G. On the basis of this concept, partial derivative gives this. Okay. And based on this two relation, we can now find that sigma is equal to del G del sigma. P and D are related to sigma and sigma u, that is the, but negative of epsilon I j is nothing but del G del sigma j. It's a negative, means negative of del G del sigma j is nothing but epsilon I j, that is the what uh, strain. Okay, strain value. You can also see here also that entropy gives and strain gives del G del capital Xi, which is also property of del C, particular del C, which depend on the SDT electric field. Okay, so this and its negative form, this. Okay, so this is a strain. It can be expressed in Xij also. That is capital X, small xij, capital Xij. And its strain is sigma ij, two rank tensor, second rank tensor. This is also second rank tensor. Okay, so the answer will be this, negative of where temperature and electric field are constant. These two are constant. Okay, these two are constant property. And okay, now question number 12 has been. Now we are going to the question number 30. That pyroelectric ceramic material show the following attribute. So what pyroelectricity is? So you have already learned about pyroelectric material, that pyroelectric material possesses spontaneous polarization along the unique crystallographic direction, which may or may not be reversal. May or may not be reversal. May means when it will be reversal, then it is showing ferroelectricity. Otherwise, it is pyroelectricity itself. Okay. By changing the polarity of the applied field, if the latter is true, then pyroelectric material is also ferroelectric. Okay. Which I have told that. Ferroelectric material is true, then the material is either a single crystalline or in a cold state. Okay. So that's a that concept. Ferroelectricity in itself is the ability of material to generate a voltage when they are heated up or cooled. It's temperature dependent of the spontaneous polarization in a polar material. Okay. Due to the minute changes that atomic position. Minute changes in the atomic positions as a result of the change in the temperature. Okay. If the temperature is constant, the voltage gradually disappears due to the leakage of charges through the material or its apparatus. Change in the polarization Change in the polarization on the sample surface can be measured as a reduced current. That's the part pyroelectricity. Change of temperature induces charge. Okay. Pyroelectricity was first observed by Greek philosopher Theophrastus in 1314 BC, who found that tourmaline attracts small pieces of straw gases when it is heated. Very interesting. The tourmaline attracts very small pieces of straw and gases. Due to which? Due to the uh, induce of charge, induction of charges. First sentence is to okay, this is the history of creation. Okay. Now, pyroelectric ceramic material shows the following attributes that they show voltage development upon changing temperature. Change in temperature is always there. It is delta T. Voltage development should be there. So this is a correct answer that they show voltage development upon changing temperature. And they show voltage development at constant temperature. That's not correct. It is correct. Pyroelectric material are necessarily polar. Okay. All the ferroelectrics are pyroelectrics material. So these two are also correct. These two are also correct. Okay. Just checking whether everything is going well or not. Wait 1 minute. Okay, everything are well. Okay. Okay. Now, only two questions are left there, 14 and 15 number questions. 15 minutes. We are at the verge of the of this lecture. Problem solving session. Just two questions are there. Then I will ask that if there is any problem, you can ask me. Okay, let's try to find out the question number 14. Okay. Um, for a cubic material, for a cubic material, where A equal to B equal to C in itself, okay, the principal dielectric constants that are K1, K2, K3, these are called principal dielectric constant. Dielectric constant is a what? Complex property. Complex. Epsilon dash I, epsilon double dash. Okay. And this is tensor also. This is tensor also. Epsilon 1 1, epsilon 1 2, 2 1, 2 2, 2 3, 3 1, 3 2, 3 3. Principal means this is also we can tell K. Okay. Means K1 means K11, K2 means which is epsilon 11, K2 means K22, which is epsilon 22, K3 means K33, which is nothing but epsilon 33. Just the diagonal components gives you diagonal components gives you the principal values. Principal values. Okay. So these are the principal values and how they are related in a cubic material. For a cubic material, everything has symmetry. For a cube, A equal to B equal to C. For a symmetric cases, what will be there? This will cancel out. This will cancel out at each faces. This will cancel out at each faces. Means E12 equal to E21, E23 equal to E32, E31 equal to E13. They each are cancel out. This cancels out. Okay. Now, I am briefly discussing the relationship of finding this anisotropic, dielectric constant and principal constant. Right? D relationship you already know in isotropic material. They are parallel. In anisotropic material, D are not parallel, and E is a tensor here. E is a tensor here. Okay. So in anisotropic material, you are telling E is a tensor. Okay. So in these cases, in anisotropic material, you will consider the tensor. Okay. So E is along x direction. So what will be the D? D will vary according to the epsilon into E. This is not constant in this time. This is varying. This is varying in an anisotropic material. So D is not along x. So D will vary also in the dx, dy, dz direction. And their cross product, their dot product, their product gives you D value. So dx value means this dx value is not the value of ex. Dx is not the value of epsilon into x. It's the value of epsilon xx into ex, epsilon yx into ex, epsilon zx into ex. They are permittivity components. Okay. Now, EB, so there is nothing but E and their epsilon components, that is epsilon ij. 9 components should be there. Okay. And there are nothing but these 9 components. Nematrix for this type of form we will see nematrix notation. 3 by 3 permittivity tensor. This is a 3 by 3 permittivity tensor. And in symmetric, which is main important point. This is symmetry. This epsilon ij symmetric. Okay, means ij equal to jr. Okay. So principal axis system in general, the medium has a set of orthogonal axes along these directions. D field components follows the direction of applied electric field. This set of orthogonal axes, the principal axis system. Okay, so what is the principal axis system? There is a set of orthogonal axes. B field follows the direction of applied field. Okay, this is the main two important point, and this is the principal axis theorem. Okay, so the permittivity tensor that Ex, Ey, Ez, the principal dielectric components, that's the principal axis theorem. Not the other, we are just considering the principal values. Okay, we are just considering the principal values, means this. So according to this, the principal, where are also principal values, principal electric electric displacement value. So for isotropic medium, Ex, Ey, Z, uniaxial medium, only two components are equal, other are unequal. For biaxial medium, okay. So these are some concepts regarding this, and on the basis of this, you can easily say that for a cubic material, this is an isotropic medium, and for isotropic medium, only this option will be correct. This is for biaxial medium, okay, uniaxial medium, uniaxial medium or biaxial. This is for uniaxial. So only correct option will be this. This will be not correct. This is for uniaxial. This is for isotropic. Okay, this is also for uniaxial. Or this is unequal. Means this is biaxial. Okay. Okay, so I think everything I have I tried to understand all these questions. And this is the last question. There is a problem of pyroelectricity involving pyroelectricity. Just pyroelectricity, nothing but um, applied electric field. Sorry, application of temperature. We have temperature application. Development of charge. Okay, development of charge. So what will be the voltage generated? This charge development plus minus generates voltage. Okay. So the voltage generated. What will be the voltage generated value across a pyroelectric material? Pyroelectric coefficient is given, which is nothing but a Coulomb meter inverse meter to the power minus 2 means per unit area, per unit temperature, how many charges are developed. Okay. Uh, Thickness is also given, is subjected to a change in a temperature of 10 Kelvin. So we are giving 10 Kelvin temperature. Charge is developing 4 into 10 to the power minus 6 Coulomb per unit meter square per unit Kelvin. So we must have to calculate area, and the material has a dielectric constant. Dielectric constant is nothing but C by C naught. Okay, so you can calculate the capacitance generated. This capacitance further develop polarization. Okay, and this creates the voltage generation. So C is nothing but epsilon naught O by D. Okay, and okay, let's try to find out. Let's first, this is a non-linear dielectric. You also have learned about non-linear dielectric, non-zero polarization in the absence of electric field. Okay. So what is pyroelectric coefficient? Pyroelectric coefficient is polarization per temperature change. Means charge developed per unit area per temperature change. Okay. That is given this type of microcoulomb charge, 4 microcoulomb charge has been generated per unit area per unit Kelvin. Thickness is given. Temperature change is 10 Kelvin. Dielectric constant is also given. So all these values are given. You have to find V, and you know this dielectric constant value is nothing but C by C naught, which is C equal to epsilon or C naught. Epsilon r into C naught value is nothing but epsilon naught into A by T. From there, A by C value has been calculated as a T by epsilon r. All these values are known values. And P equal to Q by A2, and P equal to Q means Q equal to CV from a capacitors. So just put the value of Q into CV, and you know A by C value you know. Okay. Just put the A by C value, please P. From there V is calculated, and PAP by C. Just put the value, everything are given. You will find out the voltage as 0.457 volt. Okay. So the answer will be 0.457 volt. Option B is correct. Okay. So you can see that only the 10K temperature creating nearly about 0.5 volt. Okay. In a pyroelectric material, pyroelectric cases. So temperature has a great role. Yes. Okay. Temperature has a great role in creating the voltage. Okay. So, okay, it's already 7:56. We are at the part. Only few minutes are left for completing. So I have discussed everything. I am just checking that everything has been solved or not. So question number 2, 3 is solved, 4 is solved, 5 is also solved, 6 is also solved, 7 by 4 8. Yeah, so question number 10 is okay. 11 is also okay. 12 is also okay. 13 is also okay. Okay, I have done it. 14 is also done. 15 has also been. Okay. So I think I have okay. Okay, so I have discussed all the question. If you have any question, you can ask me in your message section. Is 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 there any question on any? Please tell is there any question on whatever you have any problem, you can ask me in your message section. Okay, okay, okay. So let's uh okay, so that's it. Let's meet in the next week. We'll meet in the next week. Okay, so we can now leave the meeting. Okay, good night, everyone. See you next week. Okay, good night.